audible?
Yeah, mom.
All right. So moment of inertia we have started. We completed this. Different shapes also we have completed. We had to start with angular momentum, I believe.
Yeah, mom.
Dynamics also done. This. Sanidhi, you had to copy something, no?
Yeah, mom, the question.
This last question. First,
Yes.
then we'll start with angular momentum.
Okay, mom. Done, mom. Done, mom.
Okay, see, let's talk about the conservation of angular momentum. See, angular momentum conservation, it is related with the linear momentum. So, when the external force is zero, we say dp over dt, rate of change of momentum is zero. That's all we have already discussed. That's why I'm just writing it. And in this case, we say the momentum is constant, and that we say this is conserved. Okay. So when the external torque is zero, okay, you just relate it with this. When the external torque is zero, dl over dt is zero, means the rate of change of angular momentum will be zero. In this case, we say angular momentum is constant. Angular momentum means remaining constant means there is no change in it. That is, I omega is constant. The formula yesterday, remember, we discussed 4 points. I told you analogs where I told you L can be written as I omega. So here I omega is basically constant. Now, if you have I1, omega 1, I2, omega 2, you can simply, or in fact, not just two, why only two? For many of it, you can simply say I1 omega 1 is equal to I2 omega 2 is equal to I3 omega 3. Like this can go on. Okay. Because it is constant. It depends on what's the number given. One more thing. It is important to your aim should be this should be conserved. Angular momentum should be conserved. There shouldn't be any change in the angular momentum. But there can be change in either of the products. See, angular momentum is now made up of two quantities, moment of inertia and the angular velocity. If the angular velocity, let's say if the moment of inertia is more, angular velocity will decrease itself to make the momentum, angular momentum constant. Let's say moment of inertia decreases somehow. Radius decreases, mass decreases, moment of inertia decreases. Angular velocity will immediately increase so as to make this conserved. There won't be any change in this. This will be conserved. Like there is an example of Earth in your NCRT written, and I'll tell you one thing. This as a homework also refer to NCRT also. Means I usually not tell to refer to NCRT. Most of the things are done in the class itself, but for this you do. So this is the rotation of the Earth. So Earth is there. Earth has its own radius, and this is getting means rotated with some angle. So see here the radius is there. This is rotating with some angular velocity omega. So moment of inertia is sorry, not moment of inertia. Angular momentum is L is equal to I omega. Now see, for us, the moment of inertia will depend upon the mass and the radius. If somehow this radius of Earth increases, means moment of inertia will increase then. So if radius increases, the angular velocity will decrease, means time will be slower. It will not just take 24 hours for rotation, it will take more than that, maybe 48 hours. Time will be slower. And if the radius of Earth decreases and it becomes smaller, Earth will spin very fast. Time will be very, very, very fastly gone. One relatable example, this is not a relatable example because this doesn't happen. This is what if this happens. Relatable example is ballet dancers. That's the best example. So what do? They have their arms stretched out. Okay. They have their arms stretched out, ballet dancers, when they are moving. So when these ballet dancers are rotating, their radius is more, mass is also present, radius is more, and they are rotating with some angular velocity omega. Okay, radius is more, moment of inertia increases further. If moment of inertia increases, so angular velocity is very less, means they are spinning with a very less magnitude. What they do in order to make their dance good and so that they can spin fast, they immediately bring their arms closer to their body. Like they are dancing like this, and then they'll bring their arms closer. This will decrease the radius, that will decrease the moment of inertia, and it will increase the angular speed immediately. Like this is how you have the function. So this is moving with some angular velocity, omega. Got it? Is it clear? Conservation?
Yes, ma'am.
Okay. You write it, then we'll practice one numerical.
Okay. Done, ma'am. Done, ma'am. Done, ma'am. Done, ma'am.
See, let's practice this numerical. This says that a man standing on a rotating platform with his arms are stretching horizontally, holding weight of 5 kg weight in his each hand. Means like this. This is the person who is standing on a rotating platform. Okay. And arms are stretched out. Okay. And not stretched out. In fact, they are holding weight. This is 5 kg. This is 5 kg. So holding 5 kg weight in his each hand. Angular velocity of the platform is given. So obviously if the platform is rotating, if the platform is rotating, the man will also rotate with the weights. They will also rotate. So this is 30 RPS. Okay, 30 rotations per second. RPM, okay, per minute. RPM means per minute. So you'll have to convert it into radian per second. And I think that's not a tough task now. It says the man then brings his arm close to his body with a distance of each weight from the axis changing from 90 centimeter to 20 centimeter. Sanidhi, can you tell me what would have been the initial length here? Length of his arm.
Or
How much? Yeah? See, read the sentence. The man then brings his arm. Then tell me.
initial would have been 90 centimeters, and when he brought it close, it was 20.
That's what I wanted to hear. This is R1, 90 centimeter. Now he brings his arms closer. Means the person is there standing on the rotating platform. He has brought his both arms closer to his body. Means the weight will not change. This will still be 5 kg and this will be 5 kg. Okay, the weights will still be 5 kg. Now see here the radius that is present. This R2, this is 20 centimeter. Now omega is there, R is there. We have to, it says moment of inertia of the man together with the platform must be taken to be 7.6. Moment of inertia of the platform plus man is given as 7.6 kg meter square. That's given. It says what is his new angular speed. Means if this was omega 1, 30 rpm, what is the velocity here? See, basically, there is no external torque acting. So we know one thing, there is conservation of angular momentum. Conservation of angular momentum is there. So L is equal to I omega, which is the formula for it. So initial, for this case, let's say some angular momentum is L1. The angular velocity here is omega 1. L1 is the angular momentum, omega 1 is the angular velocity. Moment of inertia will not be a single value. See, you have four things, four systems are there, four objects are there in your system. One is the man himself who is holding the two weights. Another one is the platform. We could have neglected the platform, but the platform is the part of the system as it said that moment of inertia of the man plus the platform. Then you have this 5 kg weight. Then you have this 5 kg weight like this. Man plus platform. If I take out this moment of inertia's value, man plus platform is given to us. Let's say IP. Platform plus man, this is IP, that is 7.6. So these are included, man included, platform included. About this 5 kg weight, we have to calculate. Mass is 5 kg, radius is given. Moment of inertia is mr1 square. Then for this, so this is done. Then for this one, this will be plus another mr square. This is also done. So angular momentum will be IP plus mr1 square plus mr1 square, the moment of inertia into omega 1. Till here, have you understood?
Yes, ma'am.
Okay. Second one, in this case, see, angular momentum L2 will be equal to I into omega 2. Now, momentum, when we talk about the conservation, not momentum, moment of inertia. Still, man will be, see, you will be considering the man and the platform. So that is IP plus. For this 5 kg weight, it will be m, but radius has changed. So we will take some r2 square, this 20 centimeter. Again, for this also, we are going to take plus m r2 square. Finally, we get this now. L1 is equal to L2. So what you do, you combine both of these. IP plus, we can say m r1 square plus m r1 square is 2m r1 square equal to, this is IP plus 2m r2 square. Sorry, I forgot to write velocities. Omega 1 into omega 2. Look, from here, only few things are missing. Omega 1 is given to us, IP is given, mass is given, radius is given. IP is given, mass is given, new radius is given. Only this is missing. Will you be able to calculate? Understood?
Yes, ma'am.
Write it. This is a very important and a very good question. Please write it.
Done, mom. Done, mom. Done, mom.
Okay. See, now there's a small topic which is radius of gyration, and it's a very, very easy topic. Basically, there will be a point in your system. When we talked about moment of inertia was calculated from the entire separation or R we used to take from the axis to the final, right? So, moment of inertia was that I is equal to mr square, the formula that we use in this mr square. We never specified r that it will be from this point to this point like this. Correct? For moment of inertia, what did we used to write? R is the separation, mr square like this. But if I say there is a center of mass, or wherever the whole mass is supposed to be concentrated, let's say this point anywhere, that separation from the axis, and it can be anywhere. If I take a point here, it can be here as well. That is known as radius of gyration, and this is the only difference. Otherwise, formula is also not different. I is equal to mk square. I is equal to mr square. I is equal to mk square. I'll read it. It says it can be defined as the distance from the axis of rotation at which, if the whole mass of the body was concentrated, its moment of inertia about the given axis would be the same as with actual distribution of mass. This is the only difference. Okay, got it, Sanidhi? The difference, radius of gyration and moment of inertia.
Yeah.
Like one example, this says radius of gyration of a disk of mass. By default, when nothing is mentioned, then disk is present and the axis is there. So moment of inertia will be mr square by 2 by default for this one. And I is equal to mk square. So both of these will be equal. Mr square by 2 equal to mk square. Will be cancelled. K is equal to r by root 2. This is the radius of gyration. This is what you have to do. Like one more question. ये देखते हैं. Calculate radius of gyration for sphere of mass m and radius r. By default, when nothing is mentioned, we always assume that this is a hollow sphere. So I is equal to 2 by 3 mr square, and moment of inertia is mk square. So you equate them. 2 by 3 mr square is equal to mk square. So mass will be cancelled. K is equal to r root 2 by, got it, Sanidhi?
Yes.
Please copy down this. Now a very small portion is there. In the next class, this will be over, and in the same class, I'll start with gravitation also. Please write.
Okay, ma'am. Mom, can you tell me a place where I can find questions to do for all the chapters, like revision?
Take this book, SL Arora of class 11th, volume 1 and 2 are there. Take this, or there are plenty of questions in this. When he solved examples, many questions are there.
Okay.
Sanidhi, just you can copy this in the next class, okay? Before we
Okay.
start, first you copy. Then, okay. All right.
Yeah.
Thank you.
Thank you, ma'am.
Sanidhi, you will be having the weekly test the next week. So the center of mass and all these topics will come. Okay.